All right, this is 2-2. We're starting with polynomial functions. Let's talk about this little box right here. Okay, we talked in the last section about maximizing area given a perimeter, right?
Yes.
This is kind of the same type of thing, except three-dimensionally, we're dealing with volume instead of area, right? So maximizing volume, all right? So we're given certain dimensions of, like, let's say a piece of cardboard, and we know, like, that this is 24 inches right here, and this is 30 inches. That's all we're given. We're given a 24 by 30 inch, like, rectangle. Got it? But we have to determine how much we're going to fold it up on both sides so that we can maximize the volume, right? Like the volume, okay? So let's talk about where they get this information from. 24 minus 2x. This base right here, if we know the whole thing is 24, I have x notched out and x notched out. That's going to fold up to the sides, right? So this base right here is 24 minus 2x. Got it? This guy is 30 minus 2x because I have these guys notched out on the side. Do you see where that comes from? Okay, so my entire volume is length times width times height. The height is going to be x, the length and width are 30 minus 2x and 24 minus 2x, yeah? So I want to find the volume. When they multiplied all three of those together, they got this cubic function because we have three dimensions. So we have x cubed, okay? And they want us to find the maximum volume. We graphed it, they graphed it, and we find that the maximum volume occurs at like there-ish. You see that? Okay, what's the x coordinate right there? 4.14. Should we just say 4? We'll just round it off to 4 nicely. And then what is the volume at that place? Because that's what this coordinate over here. What? 1400. So volume is approximately 1400. Now, can I go back through and find the y coordinate? Like what the other dimension is?
Yeah.
Probably, but
no, there is no y. There is no y because we're just notching out x the same amount on each side, right? Yeah. So if I'm notching out, let's say 4 inches on each side, like this is 4 right here, this is 4 right here. How wide is this piece? 16, right? Because this is it's notching out 8, so it is a 16 as my width. Okay, what's the length?
22.
By 22. It's a 16 by 22 box. Does that make sense? Ish. I'm guessing that my x coordinate is a little bit more than 4 in that case, but approximately that's what it is, right? But what we're doing is we're multiplying all those dimensions together to find the volume and then finding the maximum of that, which is the highest point, according to what my volume is. Got it? Okay, that wasn't an actual problem. They're just showing you like this is my introduction, right? Polynomials. Let's go to the easy stuff. These are different polynomials. This is a 5th degree polynomial. And yeah, let's do that. Let's say degree and the leading coefficient. My algebra kids are doing this right now. What's the degree? Oh, I said 5th degree. What's the leading coefficient here? 4. Okay, what about this guy? He is technically a polynomial. Like y equals 2 is a polynomial. What's his degree? 0. What's his leading coefficient? 2. 2 is his leading coefficient, okay? This linear function right here is a polynomial, okay? He's in like the umbrella of polynomials, right? Here's my umbrella. Polys. We have constant functions, and we have linear functions, and we have quadratic functions, and we have cubic functions, and we have quartic functions, and we have quintic functions. And we have x to the 6th, then x to the 7th, then x to the 8th powered functions. What does not live under that umbrella is things like square roots. So put this up here. Not polys. Not polynomial functions are square roots, absolute values, cubic roots, 1 over x. Also, x to like the negative 3rd power is not a polynomial. How's come x to the negative 3rd power is not a polynomial? This equals 1 over x cubed, not polys, right? Also, not a polynomial function in one variable. They will say like x times y. That's not a polynomial, okay? Because there's 2 variables going on there. Yeah. Okay?
Can you zoom out a little bit?
You betcha. Okay? That's supposed to be an umbrella, by the way.
Yeah.
if you can't tell. I need to add my little.
Wait, what's not? And
There you go.
Dot mean?
There you go.
Like, why is there
Not polys.
Like, why is there a dot?
I don't know why there's a dot there. This dot?
I didn't know if it like stood.
Nope, not polynomials.
It's just because like if like I remember that because I do it all the time when I'm at on text, I put a period after every single thing.
Yeah, right. Yeah, sure. Yeah. Okay, so let's go back to this linear function. What is, like right here? You see where I'm at? Right here? What is the degree of that linear function? 1. What's its leading coefficient? 3. What about the quadratic function? Degree? 2. Leading coefficient? 4. Be careful because sometimes they will be nasty to you and not put them in order. Okay, so just make sure that they're in order first. Whatever, right? Okay, this is not a polynomial function.
Oh wait, go yeah.
Oh, there's one thing that I didn't put under polynomial functions.
Is that?
What is it?
Eyes, because it has an eye in the other one. Okay? Okay? So over here, this not polynomial. This is bad, this is bad, this is bad. The x squared is fine, but not polynomials for those 3 reasons. That makes him not a polynomial. Whatever. Okay? There we go.
Wait. Whoa. What page are we on?
What you talking about?
We're on the front page.
We're on the first page. We're partway down the first page, right here.
Oh, I was like, wait, what?
Okay?
Hang on. Oh, I didn't even see that. I was looking at you. My bad. I'm sorry.
All right, what kind of function is this little graph right here? He's a constant. Okay, what about this guy? Linear. What about this one? Quadratic. Okay, those are all under the umbrella of polynomial functions. Got it?
Hang on. Wait. I'm a little behind.
And the little green box down at the bottom says a 3rd degree polynomial is cubic, a 4th degree polynomial is quartic. We knew that already, right? Hopefully.
Yeah.
Okay.
Wait, what does D and LC mean?
What?
Degree.
Degree and leading coefficient.
Okay. Yeah, degree. Oh, yeah. What were we circling?
The bad things. Why is not a polynomial function?
This and this and this.
Yep. Okay,
Wait.
I'll go back to it. Back page. Smooth and continuous. This is a polynomial function. This guy is not a polynomial function because he comes to a sharp point. What is he? Absolute value. So he's not a poly. Not a poly. Okay. He is not continuous. This is not a polynomial function. Do you know what he is? 1 over x. That's what he looks like. This is not continuous. What is he? He's not a polynomial function either, but what is he? He is, yeah, he is kind of annoying.
Starts with a P. Piecewise.
He's a piecewise. P-I-E-C-E-W-I-S-E. There's no way, yeah. Did you say that? Yeah, he's a piecewise function. There's no way of graphing that without having 2 pieces. He is a quadratic and a linear function, but he has 2 pieces.
The only one that's poly.
Okay, the first one's the only one that's a polynomial.
What is
He is, what do you think he is?
a negative x to the fourth. X to the fourth.
Negative x to the 4th. He has to at least be x to the 4th. We're going to talk about that here in a second. He has to at least be x to the 4th because he has 3 humps. 3 hills or valleys, I should say. 3 maxes or mins, right? So he has to at least be an x to the 4th power in order to have that many maxes and mins. Make sense? An x squared function only has 1 hump, right? 1 hill or valley. Because he's a parabola, right? Yes, ma'am.
All the other 3 are not.
The other 3 are not polys. These are not polynomials. Okay? All right. Beautiful, beautiful. Okay? These are talking about infinite behavior. So they're talking about like end behavior. end behavior. Okay. I always write out end behavior as x goes to infinity, the y is doing something. As x goes to negative infinity, the y is doing something. Do you remember doing that? Yeah, they're not too bad. They're not too bad.
What class have you learned these in? Go up, go up, go in.
Go up, go up, go up.
Okay.
Okay.
Don't go.
I'm not going to go anywhere yet.
Yeah, because I remember I have to write so much. Like you have to write x, infinity, y, this, y, every single time.
You betcha. You betcha. Okay. Can I move?
Yeah.
I can move? Okay, I'm going to go down here off to the side. Let's put some stuff down. Okay, so let's put like y equals x. He is linear. Let's do a little rough sketch of what he looks like. And then over here, I'm going to do quadratic. We're just going to rough sketch these off to the side. I know you guys know what these look like, but we're just going to rough sketch them, okay? Quadratic, cubic, put them exactly in that order. I want these ones on the left and those ones on the right.
Aww.
Or what?
Cubic, quartic. What did you say?
Or what?
Put them in this exact order. I want the odd ones on the left and the even ones on the right. For that reason. Quintic. Y equals x to the 5th. I'll do y equals x to the 6th. He doesn't have a name for him, but we'll put him over there. Okay, and we can keep going on the pattern back and forth. Okay.
We need to pause.
I'm pausing.
Can you zoom in that way? Can you zoom out?
Zoom in that way. I can't zoom in any more than that. I think that's it. That's a 5, by the way. Okay. Yes, dear. What is it? What is being reviewed today?
Like $1.
For Teddy Grahams, but sprinkled on. Okay. Are we ready? Linear, what's he look like?
Line.
A line. I'm going to use a different color. Line. Okay. Quadratic.
A zoo.
A parabola. Cubic.
Yep, a zoo. Okay.
Do you guys know what cubic looks like?
No.
The way that I remember cubic is he's like a parabola. So if I would do that, but I flip him down. You see that?
Oh, where?
Yeah?
Wait, so which one is it?
That's what he is. It's like I took a parabola. I did one of these. Ready? Right? That's what he looks like. Okay, here's my parabola. That's what x cubed looks like. Got it?
Yeah.
Oh. Quartic. What does he look like?
0. 3 humps.
He a lot of times will have a W. Okay? Quintic. This with an extra hump.
Wow.
X to the 6th power. An extra hump. Okay? Now, he does change a little bit, like his humps might be higher or lower depending on what comes after the x to the 6th power. That determines the humps high and low and all that good stuff. Okay? So, whatever. That's what happens to him. Okay? Now let's talk about, those were all positives. Let's talk about negative. What does a negative do to it?
Flips it the other
He flips it the other way, so he's going to go like this. Negative for this guy is going to make him go like this. Okay? Do we know this?
Hold on.
Negative for this guy is going to make him go like this.
You're going way back.
He doesn't have to look pretty. Just do that to him.
Flip the line the other way.
He just makes him go downhill.
Okay, no, you can have it. It's okay. I got it. Hold up. Wait a minute. It's a chocolate.
What?
Ellie understood the assignment. I did.
Was that a TikTok? Alright.
That's the sound.
There's a reason why I had you write these ones on the left and these ones on the right. What do we got going on here?
Odds and evens.
Odd powered functions. Odds on the left, evens on the right. Okay, what does odd mean as far as end behavior goes?
You're gonna have both directions.
Opposites, odd and opposites. Okay, they are going opposite directions. So they're either going like this or they're going like this. That's odd functions. Even functions like x squared, x to the fourth, x to the sixth. Even means they're going the same direction. So they're either both up and up or down and down. Do we know that? Is that something that we know already? Maybe?
Yes.
Okay, or should?
Pretty
Okay,
self-explanatory.
self-explanatory. Okay, that is essentially what this box is telling us, right? This first box, let's just circle him. Okay, this guy. If I circle this guy, is he odd or even? Even. Is he positive or negative?
Yeah,
Positive.
Positive. This guy, odd or even?
Even.
Even. He is
Negative.
negative. Odd or even?
Odd.
Odd, positive or negative? Positive. He's going uphill, right? Odd or even?
Odd.
Odd,
Negative.
negative. Do you see how that works?
No.
Like that's what those guys are? No? No? Okay. Even means they're going the same direction. So the fact that these two are both going up,
Oh,
yeah? And he's positive because he's going up. These are both going down, so he's negative. These are going opposite directions, which means odd, uphill. Opposite, well, odd, opposite directions means odd, going downhill,
so you
negative.
just look at the last one.
Yeah, you're just like, so we don't care about any like humps and bumps or anything in the middle. We're just talking about the ends of them. Okay, which are any end behavior, right? So this guy, A and B, we're gonna go through and like do a little rough sketch of him. I don't care what the humps and bumps look like in the middle. Okay, so A, I'm gonna do that over here, and I'm gonna do B over here. Okay, A, the only thing we look at is the degree and the leading coefficient. Okay,
5.
so the degree is 5, so he is an odd function, right? And the leading coefficient is -4, so he is negative. He's odd and he's negative. Okay? Odd means opposite. So we're going opposite directions, and negative means we're going downhill. So if I rough sketch what he looks like, he's going downhill, he's going opposite directions. So like maybe like this. I don't care how many humps and bumps he has in the middle, but that's what he's going to look like essentially. Okay? Then we fill out the end behavior. As x goes to infinity, the y is going to something. Okay, we're going to fill in those blanks here in a second. I'll slow down.
Yeah, I hate these things. You need like a stamp that has
I know, I should.
like you have.
I should get a stamp. I have the sine, cosine, and tangent one.
Just because
I wonder if you can order those.
you could probably have them made like that on Etsy. What's it called? And behavior stamp.
Well, I bet you can just order, like, you can go onto a place and say, I want a stamp made, and you can insert your own, like, PDF or whatever, and it will, like, make that stamp, you know?
I'm sure. Yeah.
I bet you it would do that.
Or I'm sure you could just like.
How'd you get your cosine one?
Luke's older brother gave it to me. Because I was complaining about it one day, and he's like, here you go. I'm like, oh.
Here.
Sorry.
You want to use it?
What?
You actually use it? Amazon.
I don't use it as much as I used to, because I used to have a dot camera where I actually had to write out my notes and I would stamp it, but some of my kids use it. They'll stamp it on their papers and stuff. It is kind of a big stamp, so they usually just use it like on their homework assignments as long as they leave enough room. Whatever. Okay. All right. So when we fill out end behavior, it looks like this every single time, and the only thing we do is fill in the y's. So as x goes toward infinity, this is a fancy way of saying as my function goes to the right. What's on the right side of my graph? Negative. He's going down on the right side of my graph. What about on the left side of my graph? He's going to positive infinity. That's my end behavior. Okay? Good? Buh. What the
So,
heck
question,
is
question,
B
question.
doing? What?
For an odd function, like, will the infinity always be negative infinity and then negative infinity always be infinity?
Not always. But for an odd function, these two will always be different symbols.
Okay.
Does that make sense?
Yeah.
If he would have been positive, it would have been flipped the other way around. Does that make sense?
Oh, okay.
Yeah? Yeah? Okay. All right, B. Oh, heavens. What's the degree?
To the fourth.
Or no, to the third.
What?
Well, then you have to take that times x.
If I would FOIL it all out, what?
Well, all of it is.
It's the highest, well, that's if, like, I'm looking at my, like, terms. This is not multiplied out. I would have to multiply it out. If I would multiply it out, what would be the highest power?
6.
There's 3 here. This is to the third. This is to the second, technically, and then there's 1 here. So if I were to multiply them all out,
7.
my first term would be to the 7th power or whatever, or 6th power, sixth power, okay? So the degree here would be 6. He would be an even function, okay? The leading coefficient. I don't necessarily know the leading coefficient until I multiply it out. I could figure it out, right? 1/4 is this number is 2, this number is 1. But this number is really not 2, this number is really actually
36.
8. Because 2 to the 3rd power is 8, right? So this number is actually 8. This number is 1, or 1 squared, which is still 1. So 8 times 1 times 1/4, my leading coefficient is 2. Do you see how that is? Okay? If that doesn't make any sense to you, we only care about the leading coefficient being positive or negative. Is it going to be positive or negative?
Positive.
Positive. There's no negatives in there for my leading coefficient anyway. The -3 is not going to affect it, okay? So my leading coefficient will be positive, okay? That's all we really care about. It will actually be 2 if I multiply it all out, right? But he's positive. So he's even and positive, which means he's going up and up. And I don't care how many humps he has in the middle, he's doing one of those. Then we fill out our end behavior.
Both to infinity.
Yep.
She asked.
I'll just fill it in. There you go. There's my end behavior. Determine the end behavior. So when they ask for that, you're just filling in that little thing right there. On the right side of the graph, he's going up. The left side of the graph is going up. So infinity, infinity.
Why do we go right to left? Why do we go left to right?
Maybe. I
Why?
don't know. I always just start with infinity. Like on the right side and on the left side. You could go either way. I don't care. And in fact, a lot of people do. That's probably why, because they want to look at the left side instead of the right side. I don't know. Yeah, sure. If you put this part before this part, it's fine. Yeah.
I would
Like
say
Reese wants to
read
do the
it.
Reese wants to do the left side first before she does the right side. Does that make sense?
Why would you do that?
Because that probably makes more sense
Because you
actually.
read left.
That makes more sense than what I do. What?
Because you read left.
Yeah, I know, right? Exactly. You read left to right. That makes more sense than what I was doing. I don't know why I do that.
Degree.
I just always do I have positive infinity.
Yeah, wait, can you go back down? I just need to look at the.
See, they do it here too. As x goes up. Maybe that's just because I'm used to like looking at the textbook. They always say infinity and then negative infinity, which technically it should go the other way around, left and then right. I don't know.
Wait, can you?
I'm holding up.
In November. We should have all it there.
Call it a day.
We have like a long time yet.
We have a long
Let's go to. I want to get to. Oh, because we have so many pages left. I want to get to example 3. We'll do 2 more examples, then we'll stop. Okay. Actually, yeah. Okay. All right, we're on the second page. The next page? Not the second page. The third page. Identifying zeros. What's a zero? Let's talk about that first. The x-intercepts. Okay, x-intercepts. And then, have you ever heard the word multiplicity before? No.
multiple. I don't know.
Multiplicity. Okay, so let's go back to like quadratic functions. Let's say I have a quadratic function where I have y equals x plus 2 squared, right? Let's go x plus 3 squared so I don't have too many 2's. X plus 3 squared.
Teachers, please dismiss the junior high girls basketball players.
Goodbye, junior high girls basketball players. Hey, Jack, did you ever figure out your basketball stuff?
No.
Okay. Have they come in? No? Okay. Okay. All right, let's say we have this going on here, right? This is technically in vertex form. He's like plus 0 on the end here, right? Okay. So he is a quadratic function. And where is the vertex located? What? Negative 3, 0. 1, 2, 3, 0 right here. And he goes like this. Okay? Got it? Does that make sense? Okay, if I would solve for the zeros, I would plug 0 in for y, and then I could take the square root and subtract the 3 and all that good stuff, and I would get that, right? Okay? He only has 1 0, or one place where he touches, right? Typically on a quadratic function, you could have 2, or you might not have any. This one has 1, yeah? Okay? His 0 is negative 3, but negative 3 has a multiplicity of 2, which means, boys, are you listening?
Yep.
Negative 3 is my 0, and he has a multiplicity of 2 because it's squared, which means that negative 3 is a double 0. Does that make sense? He's a 0 twice. Okay?
And
Really, if I want to write this out,
We
this
have two y-intercepts.
this can be rewritten as x plus 3 times x plus 3. Do you agree? That's what x plus 3 squared is, right? And if I set this guy equal to 0, x equals negative 3. And if I set this guy equal to 0, x equals negative 3. So negative 3 is an answer twice. He has a multiplicity of 2. Okay?
So
Here's what multiplicity does.
Oh, no.
Are you ready? A lot of times you'll have an answer just show up once, so its multiplicity is 1. So like here, y equals, let's say I have x plus 5, you don't have to write this down, and x minus 4. Okay, if I have x plus 5 and x minus 4, that means x equals negative 5 and x equals positive 4. This guy has a multiplicity of 1, and this guy has a multiplicity of 1. You see that? Because they're only showing up as an answer once, right? Versus this one, negative 3, shows up as an answer twice. It's like a double 0, okay? So it has multiplicity of 2. If it has an odd multiplicity, like 1 or 3 or 5 or 7, it's showing up as an answer once. It's showing up as an answer 3 times. It's showing up as an answer 5 times. If it has an odd multiplicity, it's going to cross the x-axis at that point. If it has an even multiplicity, like this one, it's going to come down, touch, and then go back. Let's see what I mean. This guy had a multiplicity of 2, which means he is a touch point. He is not a cross point. This guy touches. He does not cross. Does that make sense? Because he has an even multiplicity.
So if he evens, he is a point, and if he's odd, he's a cross.
If he's an even multiplicity, he's a touch point. If he's an odd multiplicity, he's a cross point. So let's say like y equals x minus 5 to the third power. Okay, if I would do all of that stuff out, I would end up with a cubic function, right? And this is like x minus 5 times x minus 5 times x minus 5, right? So I have x equals 5, x equals 5, x equals 5, essentially, right? So it has 5 has a multiplicity of 3. It's showing up as an answer 3 times, which means at 5, 1, 2, 3, 4, 5, he's going to cross. And he looks like this. That's a cubic function. And he's crossing at 5. Does that make sense?
Oh, okay.
An odd multiplicity crosses, and even multiplicity touches, right? Like this guy was negative 5 and 4. He was a quadratic function at negative 5 over here and at 4 over here. He is crossing because he had multiplicity of 1, which is an odd multiplicity. Odd means cross, even means touch. I don't make up the rules. That's just the way that it works. Okay, so let's go through this guy. Finding the zeros of the function defined by this. I want to find the zeros. He has 4 pieces. There's only one thing besides the ugly method, which we haven't learned yet. One thing that I can do if he has 4 pieces to like break him down. What's this called? Grouping. Factor by grouping. Okay, if I group them and I pull out, what are you going to pull out of the first piece? X squared, okay. Left over is x plus 1. What are you going to take out of the second piece?
3, 9.
Negative 9, and left over is x plus 1, right? Because you're taking the negative out, okay? Now my 2 bubbles, x plus 1 is what they have in common, okay? If I take that out, I have x squared minus 9 left over, except we're not done factoring.
Because that's a difference.
This is the difference of squares. What's x squared minus 9? X plus 3, x minus 3. It doesn't matter which order you go in. Okay? All right, so what are my zeros going to be?
Negative 3, positive 3, negative 1.
Negative 1, negative 3, positive 3, whichever order you want to go in. What's the multiplicity of each one? How many times is negative 1 showing up as an answer? Once. How many times is negative 3 showing up as an answer? Once. How many times is 3 showing up as an answer? So each of those points, my graph is going to cross at. It's going to cross.
Because
Cross.
Yeah.
Right? That's what he will look like. This is doing this. Cross. Right? Wherever those are at. Negative 3, negative 1, and positive 3. My y-axis is not in the right spot, but whatever.
Wait.
Blip, like that. There you go. Ish. That's what's happening. Cross, right? Okay. All right, last one. Determine the zeros of this polynomial function. Let's break them down. What shall we do?
Take out an x.
Take out an x. I'm going to take out
A negative x.
a negative x because I want that one to be positive. So let's do that. Negative x. Left is x squared. Then what?
Minus 4
Minus 4x
plus.
plus 16. Okay? Now, what is this thing right here?
Wait a minute. Why did we do that? Why 4x?
How'd you get?
What? Oh, you're right. I can't math. 8x. Because I was already thinking the next step, because guess what the next step is?
Take out a 2.
Nah. No, you're breaking them down. What can you multiply to get 16, but when you add them, give you negative 8?
4.
X minus 4, right? That's him broken down. Okay, so now what do we do?
It's, oh, we still have an x in the front. X equals 0.
Negative x equals 0, which means if I divide by negative 1, x equals still 0. What's his multiplicity?
Nothing.
1. He only shows up as an answer once, okay? This guy, if I set him equal to 0, x equals
4.
4. What's his multiplicity? 2, because he's going to be the same there, right? So here is where he is going to cross, and then he's going to touch right here. He is an x to the third power function. At 0, he's going to cross. At 4, he's going to touch. You got any ideas what he looks like?
Okay, say that again.
At 0, he's going to cross. At 4, he's going to touch. So cross, touch, up. That's my x to the third power function. Make sense? Okay, multiplicity tells you that. If he has an odd multiplicity, he's going to cross. If he has an even multiplicity, he's going to touch. Right, Jake? He's like, I don't even remember this at all. Yep. Okay, we'll stop there.
Wait, can I borrow your
'Kay.
iPad? I'm a little behind this.
Here's the homework problems if you want to get a start. It wouldn't be a bad idea.
Oh, I need her to explain.
How many can we do?
Comature, can you help me?
Oh, I should probably write the homework problems down. Connor, because Connor might not have the homework problems. Page 199, 16, 18, 24, 28, 30, 40, 46, 48, and 53 through 58. And we can get through, I don't know,
Here you go, Comature. That's a
identifying
lot.
zeros and multiplicity of zeros.
Why so
You
many?
can get through 38.
Comature, I need you to
So like
explain
right
this.
here, 30. So you can do the first 5. There you go. Okay? All right. Very good.